I would like to share some of the experiences I had during my journey of around 3 decades, I should say, in the field of metal metals composites. So I would like to just, in coming out with a product from a metal metals composites. My outline would be issues in designing an appropriate composite. So we'll look at how to come out with an appropriate metal metals composite. So it definitely depends upon the application. So for example, you're looking at an application like piston. So there the main thing here is the CTE. So we need to focus on the CTE mismatch between the matrix and the reinforcement. So I think most of us need to really pick up some of the physical properties of the reinforcement together with the matrix materials that are available, that are being studied, and that is how we need to really do a lot of groundwork before we decide the appropriate reinforcement and so on. For example, if you're looking at silicon carbide, the most widely used, what happens with the CTE of a piston, what you make, or oil compatibility. So that's another issue if you're looking at. The other key issue is about the tribological aspects. We do not want the secondary particles to be protruding out of the surface. So what happens here is when you're talking about a piston on which you have a sealant, on which you have the oil, the problem there is there's going to be a welling out of your sealant because of the protruding particles. So that's a real challenge in fact. So this needs to be really addressed when we're talking about the end component. So we need to first identify the end component, look at all the operating parameters, and come out with the actual property requirement. It may be physical, thermophysical properties, and also the mechanical properties. When again referring back to the piston again, the properties, elevated properties. So we need to look at the operating temperature. For example, we're looking around 230 plus. So you need to get all the elevated properties. As of now, you don't have database at all as regards the elevated temperature properties or elevated it can be modulus, it can be yield strength, it can be ductility. It's very, very important from the point of view of the fracture toughness. That's very important. So these issues are not at all addressed, or there is no database at all to really say this material really qualifies. So that's where we need to be move with a lot of caution in coming out with an appropriate composite for a right application. So next is about the processing. That's another major challenge when you're talking about a component. So as I told again, when you're talking about piston, so one of the days when they're talking only about forging. So today people are talking about casting, then you have the extrusion, and then the forging, because they're talking about a pressure tightness. So it's very, very important when talking about pressure tightness application. So you need to ensure that you have a minimal defects. So what is that minimum defect in the sense we are talking about in metal metals composites is number one, agglomeration. So how do you ensure that you get the best of the best distribution? That's the challenge. It can be by powder metallurgy, it can be by squeeze casting. Majority of the production route for the component, all people are now trying to look at squeeze casting because we can go for high volume fractions and so on. But then processing is a very, very important route, because once you have the casting, you also need to go with the extrusion. Now, extrusion is really a very, very challenging one when you're talking about a metal metals composite. And next comes the forging. This is yet another major problem. When you're talking about high strength alloys like aluminum copper alloys, 2014, which is having the least CTE and which is being popularly used for the piston materials. Look at them, they are having a strength of around 434, close to that MPa is the strength you are talking about. And those high strength material, when you are doing forging, you need to be very, very careful about the processing temperature. Is it 475 or 470, 500, something like that. If you fail to adopt a perfect processing parameters, or what I mean to say, a processing map, you don't have a processing map for forging, you don't have a processing map for extrusion of these alloys, and then the composites, it's very, very difficult to really say, look, you have to work on within this range. It's very, very difficult, because we have really experienced this. once you do at around 500 degrees centigrade, you get only cracked material, you don't get a quality forging at all. So that's a very, very important thing. And in that situation, when you're talking about a metal metals composites, look, we are talking about heating and cooling cycles in all these thermomechanical processes, and that's where we are in, and we have still not looked at what are the stress and strain around the particle or the interface, because interfacial bonding is a key issue in all these processes, because if that interfacial bond really fails, again we'll have a lot of problems when we're talking about the product. The next issue which I would like to dwell upon is in the joining. So as Professor Shamram rightly pointed out, when we're talking about laminated composites, polymer composites, again the issue is the joining. So how do you join? So in fact we had one common student who was working on bolted fastener. We are looking at fasteners, analysis of fasteners, and there are around thousands of fasteners we need to analyze. And so what we are looking, so therefore joining again is a major issue, because we are looking at three aspects. In that case it's the interlaminar shear stresses and so on. But in case of my metal metals composites, it's very important that I focus on how to ensure that I do not allow re-agglomeration. It's already agglomerated. How do I minimize the agglomeration? A. B is how do I eliminate my defects, especially joining. How do I get a perfect joining? So we have in fact tried out with the EVM. In fact, we wanted to make cycle frames. We were successful in making a tube. We had a mandrel. We used our 200-ton press. We got the tubes, and on that we did anodizing. Anodizing again was very difficult. So that's what I will be addressing on the surface treatment of the composites. So we were able to get very good finish, of course, and then, but we were not able to get the joint. So if you look at today's new cycles, you pay around 3 lakh. It's all aluminum frame, and you've got a very good welding. But then, when you talk about these lightweight structures, it's very, very difficult to really get the joint properly. So that's where we need to focus, especially in coming out with the right product and talking about the composites. So next is about us. So we have been, of course, in my lab, we have been successful in these two areas, like torpedo blades and piston, which I'll discuss later. And people are now trying to move from particulate reinforced. Of course, particle reinforced, normally they give nearly isotropic, if not exactly isotropic. But then today people are again, because looking at high modulus application and so on, people are now moving again getting back to developing high quality carbon fiber composites. So that is the trend, and in fact people are looking at carbon fiber rods. You are getting 2 mm, 1 mm and even 6 mm rods, which are being used in a lot of applications for lightweight structures, which have already got very good strength, stiffness and so on. They now people are looking at them as a very viable potential reinforcement for, especially for copper and in fact aluminum matrices, and especially people are trying to exploit in the area of heat sinks. So just proceeding, I think the surface treatment is again I would like to dwell upon. When you look at any of your aluminum composites and so on, aluminum and so on, anodizing is what normally people do prefer. And when you look at anodizing of your metal metals composites, it's again a very, very challenging one. It's very, very difficult to get a very adherent anodized layer, and again, because you can give different tinge to that color, different colors you can make it appealing to a customer if you want to sell the product. It's not just enough that I just come out with a product. It's equally important that the component should really, you should be in a position to sell the product to the customer, and so that when you're talking about the appearance wise, so it's very difficult to really get the surface treatment, the right surface treatment on that. And the other thing which I would like to tell you here is about in aerospace industries, people are now looking at this polymeric paint on these sheets, and that's another area. It's very, very difficult again, because you need to have a lot of pre-treatments on the components, whatever you make from MMCs, before you really give them a very good polymeric coating, and that's one thing, the advancements which I'm talking about. Finally, the most important thing, as all of us are aware, is I think some groups may be working is on the machinability of the metal metals composites. In fact, this is one of the worrying points, because at the end of the day, when you're talking about not just one component, it is a system, subsystem and a system. So when you're talking about assembly, It is surface integrity that is very, very important. And in fact, we were able to do some lot of EDM studies and so on. When looking at EDM and so on, what you look at here is there is going to be a damage to the reinforcement and so on. And once there is a pull out of the particles or pull out of the reinforcement fiber, whatever the damage is we are talking about, there's always going to be a deviation in the dimensions. What I say, it is going to be a bit of tapering. So you're talking about micron level, it may be 100 mm you're talking about, that can be around 98 on the other side, or even, so there's going to be a tapering. That's one major problem that we need to address. And the conventional machining, again, people are now trying to look at a lot of coated tools and so on, because when you are given a task, as I told, coming out with a finished component like piston, again tooling is very, very important, because I need to get the desired surface finish, because I need to supply my component as per the drawing. So if I need to meet those requirements, I need to have the best of the best cutting tools. So people are looking at PCBs and so on to really get the right finish. That's one major thing which we need to focus. And people are now looking towards non-conventional, non-traditional machining and so on. And when you're talking about the processing side, so there is a lot of work being done currently now regarding the ceramic powders. It can be either people are focusing more on CNTs, people are going towards the nano size powders and so on to get maximum benefit out of it. When you're talking about especially the thermal properties, it can be thermal conductivity, because people are mostly focusing on the electronic component side, like the heat sinks and so on, where they're looking at, because most of the metals composites, as you're talking about, it can be a ceramic reinforced one, you have a problem with lowering of the conductivity, whereas in terms of CNTs, that's one plus point. When we're talking about carbon fiber, again, that's a plus point. We're talking about an improvement in the conductivity. That's a major thing when we're talking about the heat sinks and so on. And so here, people are looking towards pre-treatment, in the sense it can be, they are looking at electroless coating of the powders, so which was being used long, since 30 years back. Now again, people are looking back, trying to look at pre-treating the powders with electroless coating. So all I would like to say here is to really come out with a very high quality composite for the right product you are looking for. We need to really know a lot about the fundamentals of chemistry and then mechanical engineering, as well as all the operating parameters of the product that you have in mind. And the other issue which has not been really looked at from the academic point of view is they are not focusing on how to look at large scale production. Okay, I can produce one piston, I can produce two piston, I can produce 10 piston, but I am talking about economically large scale feasible type of production. So that's where we need to really integrate, and we really need to know more about the what I should say, some sort of automation when you're talking about manufacturing of metal matrix composites, because absolutely I find that there is no attempt when we are talking about automation in terms like it can be a process parameter like simple pouring temperature, or it can be the mixing, it can be the rate at which you really you're talking about the control, hydrodynamic control and so on. Absolutely there is no control over those. We are all trying to do manually and so on. And so if efforts are there to really focus on how effectively we can control these processing parameters, I think if we can bring in some sort of automation in this, if there is some sort of a measuring element we can build in, and we can have a closed loop system, I think we can strike the right chord in coming out with a very high quality composite, and we can come out with a lot of applications which I think especially Japan and UK, they're all coming out with a lot of MMCs, especially railways. They're trying to look at bogies, discs and all those things. So that way we can look at a lot of applications. Definitely as I told, the lacuna is we need to now energize, trying to see if we can have some automations at different levels of processing. It need not be only powder metallurgy, it need not be stud casting, only just the space casting or whatever it is. So that's where I think we need to focus. And finally, the thing which I just want to, before I wind up, is about the finite element analysis. So when you're talking about the fracture toughness and so on, as I've been telling you, most we need to focus from the part as a mechanical engineer, we need to focus on the stresses. Now we need to really look at how to really adopt a finite element analysis for this discontinuous reinforced matrix, because that is where at the interface I can look at what is happening, what is the state of stress and strain at different dynamic conditions. You can study and really do a lot of dynamic tests. And only problem there is, meshing, how to look at the meshing, how to really segregate the interfaces, how to really account for the thermophysical properties of the reinforcement and the matrix, and how to really input the correct data. That's very, very important, because when you're talking about, for example, MMCs by liquid metallurgy, so I need to look at solidification. So solidification is a key issue there. So you need to really look at a procast software, for example. So you can look at that and try to understand the fundamentals, the gating, risering, and so on. Because when we're talking about brake drums, for example, in our lab we have developed some brake drums out of aluminum MMCs, aluminum silicon carbide. So all we did was we used the procast. Only thing is we played around with the latent heat and specific heat and so on, with all the rule of mixtures, and we really used it very effectively, and we were able to really get to know what is the volume of the yield. Because at the end of the day in casting, if at all it has to be economical, the yield has to be the maximum. So if at all the yield has to be maximum, so we need to use all this analysis tool or the software what we have to really get a quality composite on a large scale production. So that's one thing I think we can focus on. I think if I have time. Is it do I have 5 more? 5 more. So the other very this is about as I was talking about the finite element analysis. So especially in the area of doing experiment and then constructing a processing map is very, very difficult when you're talking about, because which we have been doing, it's very, very difficult. So whereas you have a software, deform software, I think most of us do have the deform software, where we can do a wonderful thermomechanical analysis and then try to understand the behavior of a composite material during hot extrusion, during forging, and definitely we can reduce the maximum number of, we can reduce the defects and come out with a right quality product. Because at the end of the day, in fact, experimentally from past 3-4 years, I have been struggling to really optimize like extrusion temperature, the billet, what is that, the die temperature, and then because if there is a huge temperature gradient between my billet and my die, it's going to be very difficult for you to get a quality extrude. Because at the end of the day, the surface finish of my extrude product is very, very important. If at all you have to get the right product, I mean it's a product, I mean extruded rod, remember you need to use the right type of lubricant. I forgot, this is another area which we need to work on, is the right kind of lubricant what we use. Normally they are using the graphite as a lubricant because we do not want aluminum to stick on to the die, but then there are so many advancements today, you've got copper spray, this so on, so we need to do a lot of work. So all these things you can do it on the screen and then try to understand what is happening to the heat transfer characteristics, come out with the temperature profile, and you can definitely design, I mean you can definitely design the best of the best process parameters, and then reduce your experimentation, work on that, and that's where you can definitely get a very high quality product. And in fact the die life gets improved because you have got the best processing parameters, your die life enhances. And because today, especially in extrusion, the tooling cost is very, very high. You need to spend minimum 3 to 4 lakhs just for tooling. You just have a press, it's not enough. The tooling cost is very, very important, as Professor rightly pointed out, Shambhav. So even in extrusion of metal matrix composites, it is a tooling. So if at all, so you want to reduce that, you need to really work on these tools, what we have on the deform tools and so on, and do a lot of simulations and do that. So with this, I thank the organizers for having given me this wonderful opportunity to share some of the experiences I had in this wonderful field of metal matrix composites. Thank you once again, and the house is open for
impact.
Correct.
Volumetric composites by itself is not very tough like metal, and when they subjected to the impact, either low velocity impact or high velocity impact in turbine blades, for example.
Okay.
So, is it possible that on the composite, can you put your metal matrix like I said, nanotube something, and make a composite of that, and
the whole issue here is because I have not seen any literature, because it's very difficult, because at the end of the day we cannot have a mixture of these two things at all.
What I mean, once it's made, can you, like a paint, is it possible to spray?
Spray, yeah.
Something. That's what.
Yeah, correct. I totally agree. Now we are trying to work on that. But what we are trying to look at here is for two things we are looking at. We are trying to do the thermal spraying of honeycomb structures. We have done it in our lab. That is exclusively if we take care of corrosion as well as to make it conductive. So only for two purposes we are trying, but we are not looked at the for dynamic loading. We are not
because there is one in the composite area.
From Ramesh School of Advanced Studies, I want to know about this. Basically, in MMCs, you have the problem of distribution of the reinforcements.
Correct.
So, how do you take care of it? Like, even if you talk about stir casting or squares, so basically you should have.
My answer is only thing you have to work with it, and three, four things are there. You really need to understand the chemistry, the wettability. That's what I told. Designing means you need to choose the right type of reinforcement, number one, with what matrix you are talking about. And number two is about the pre-treatment. So there are several routes, but then the currently, as I told, the electroless route is one of the most very effective one which we have been trying out. So all you can do is you can just look at electroless coating of the powders, and then definitely you'll get the best of the best this one. And the other thing is the designing of the impeller. So all you need to do is you need to ensure that the hydrodynamic turbulence, that's again very, very important. So you need to have a well designed stirrer setup. So that's very important. So you can do a lot of simulation with say water and graphite, which will simulate your aluminum and silicon carbide like that. You can do some simulation studies. That's what we did. Then we did some studies, and then say 100, 200 like that, and then we made those such impellers, and then we were able to do it. And so all we need to do is we need to have a combination of some bit of simulation and then do experiment, and then use the coated one. And also you also need to look at pre-treatment, preheating the powders again.
Machining of MMCs. The major problem with the conventional machining of MMCs is the wear of the cutting tool itself. The abrasive particle present in the MMC, that itself will reduces the tool life. So therefore people go for the coating of the something on the cutting tools. So normally even with the coating also the tool life will be very less. Without coating it will be for few seconds, and with coating it sustain only for few minutes. So the recent advancement is trying with the unconventional machining. So people are trying with EDM, LBM and abrasive water jet cutting. In fact, I worked on abrasive water jet cutting of MMCs in IIT Madras, and I know the major problem with the abrasive water jet cutting is the deflection of the jet. So jet will not deflect in the top region, that is called as cutting wear mode, and in the bottom we call it as deformation wear mode, and there the jet deflects more and the surface finish will be reduces. And people are trying with EDM and LBM also, and the major problem is the heat affected zone. And one more thing I would like to add is recently we got sanction from the TechCube regarding the Center of Excellence, and we are establishing the Center of Excellence in our college at BNC. It's about a 5 crore project. And there we are doing fabrication of MMCs, nano as well as macro, and we are doing the characterization, and we are working on machining also. So if anybody is working on these areas, and if you want to share, and if you want to join hands with us, they are welcome. And our R&D director is also here. and our full team is present here. So you can contact Srinivas or Ramchandra. We are from mechanical department of BMSC. So people working on characterization, synthesis and machining. They are welcome. Thank you.